Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, thanks. So it's good to see there are folks in the room here after lunch. So I'm Rajiv Rastogi, and I'm with Amazon. So we've recently started a machine learning group here in Bangalore. Although the work I'm going to be talking about is work I did at Yahoo with a bunch of colleagues there. And Sundarajan presented yesterday, so this is joint work with him. So what I'm going to talk about is building knowledge bases from the web, and I'll just provide a short motivation, although this is not really that surprising. Clearly there's lots of information on the web. You have sites like Wikipedia with pages for over 3.5 million entities on the web. Of course, the company that I work for has information on products and prices, and there are hundreds of millions of products and prices that we sell online. There are aggregators like Yelp that have information about businesses, and of course you have social networks that have information about people. This is pretty annoying. Okay. So clearly, I mean, it'd be great if you could mine all these websites. There's a wealth of information out there. If you could mine all these sites and maybe store structured records, about people, places, things, events in a knowledge base. So, you would now have a knowledge base that had records with information about, cameras and their megapixel values, products and their prices, businesses, restaurants and their addresses, phone numbers, and so on, and people and their affiliations. Okay. So, what's the point of having this knowledge base, right? I mean, many of the companies out there, at least Yahoo, we were building these knowledge bases to improve search, to provide much more relevant information to users. So, for example, if you looked at search in the past, users typed in a search query and the search engine came back with a search results page that contained your standard 10 blue links, right? Every page that the search engine came back with had the same look and feel. You had these 10 blue links on your search page. But with these knowledge bases, and you're already starting to see this happen with a lot of search engines, when you type in a search query, what you get back is a search result page that looks like this. Now, every URL, you have a structured abstract. And this is actually populated from this knowledge base, right? And it contains the most important information in the underlying page, right? So for example, for this restaurant page out here, right, you have information like ratings, address, phone numbers, and so on, right? So users can actually find the information that they're looking for without having to click too many URLs. The search result page itself is a lot more informative, and this leads to a much better user experience. So that's what we found at Yahoo. Of course, you can use knowledge bases, and this is the grand vision, to present to users topic entity pages. So for example, you typed in a search query for Madonna, and what you got back was not 10 blue links, but a topic entity page that looked like this, right? It contains a lot of different information about Madonna. There could be, all her singles, top selling albums, multimedia content like images, music videos, and also you could have news feeds, tweets, blog posts, a whole slew of information, right? And this is a much better user experience than just seeing 10 blue links and having to navigate through them. So what's the problem with building these knowledge bases? So clearly, I mean, this is a fairly challenging problem, right? I mean, there are billions of pages out there. These pages have very diverse structure. So for example, here you have two pages for the same restaurant called Chinese Mirch, one on Yelp.com, another on superpages.com. And in one page you have the phone number following the address, the other page you have the phone number before the address, you have some category information right on the top here, you have category information at the bottom here. If you look at the terms used to refer to categories, they are different. You call them, cuisine here, and of course it's called Asian here, and here it's called Chinese and Indian Pakistani. By the way, this is an Indian restaurant, so it's in New York. But so clearly, I mean, there's a lot of difference in structure, and also there's a lot of noise in these pages, right? That's what makes it really difficult. All the stuff out here in the middle of the page is essentially noise, and websites are putting in more and more of this extraneous information on the web pages. Okay, so creation of this knowledge base involves three primary steps. The first step, you actually acquire the content by crawling the web pages, and then you kind of take all the crawled pages, you extract structured data like maps, addresses, and so on for different entities, and that's the second step here, which is the information extraction piece. And the final piece is really integrating all this data, right? So you may have information for the same entity from multiple different websites, so you want to cluster all those different pieces of data and resolve discrepancies between them. So in this talk, I'm going to focus on information extraction, right? And how we use machine learning to actually extract information from web pages at scale. So that's going to be the primary sort of topic of my talk. So what is information extraction, right? So you have a web page here. So the goal really is to extract attribute values from web pages and store them in a structured record like this, right? So at a very high level, one view of information extraction is that you're really associating semantics with values in a page, right? And you're doing this by tagging these values with attribute labels. So for example, you're saying, well, this is a phone number, this is an address field, this is cuisine information, and so on. So at some level, these were just byte strings in your page, text strings in your page, and you're sort of associating semantics with these strings. Now in this talk, what I'm going to focus on are template-based pages. These are pages that are dynamically generated by populating these fixed templates from a backend database, right? You have records in a backend DBMS, and you use those to dynamically create the pages. Now, interestingly, these pages all have very similar structure, and if you look at Amazon.com, there are tens of millions of such pages for different products, CDs, electronics, books, and so on. And they're all dynamically generated pages with very similar structure. And interestingly, this class of pages constitute a fairly, big fraction of crawled pages out there. Pages that are being crawled by search engines like, Yahoo at that time, and Google and Bing, and so on. So what we found is 30% of crawled pages are these template-based pages. And they're also very information rich. If you look at 30% of the top 10 search results for queries, they all were template-based pages. In fact, if you give a restaurant query, 9 out of the 10 results will be all, results from aggregator sites with template-based pages like this. So this is a fairly good set of class of pages to extract from. And as you'll see that there are some properties here that make it easier to extract from some pages like this. So again, information extraction from the web is not a new area. This problem has been studied for over a decade, and there are many techniques out there for extracting structured data from web pages. And these techniques can be actually classified along two dimensions. So based on how these techniques exploit structure and content. Right at the bottom here, you have wrapper-based schemes. These primarily rely on HTML tag information, right? To extract records from web pages. And then there are some schemes that actually exploit content redundancy, right? This is basically the fact that content for the same entity appears on multiple different sites is exploited by these schemes. And the way these schemes work is they match content values across different sites to extract the structured data. And then you have, a number of recent proposals that use machine learning models, right? And these models use both content and structural features. And I'll talk a little bit more about how machine learning is being used to extract information from web pages. Recent proposals include hierarchical CRFs. This came out of Microsoft research in Beijing, and even Markov Logic Networks that have been used both by some researchers at Microsoft, and we had a paper in SIG-KDD using Markov Logic Networks as well that I'll be talking about. So these are two recently proposed models for extracting structured data from web pages, right? And then there's work really to extract information and records from unstructured text, and these are more pattern-based approaches. Okay, so let me move on to our machine learning approach. And as I said, we use Markov Logic Networks to extract information from web pages, and this is done in a completely unsupervised fashion. Okay. So what are Markov Logic Networks? Here's just a brief introduction to MLNs. So they provide a probabilistic modeling framework that's based on first order logic. So it's sort of a generalization of Markov networks. Now in this framework, a world that violates these first order formulas is possible in a probabilistic sense. Okay? So if you look at first order logic, you can't have a world that actually violates those first order formulas. But here you could sort of violate certain formulas in a probabilistic way, right? So this is really useful for our information extraction scenario because data typically tends to be extremely noisy, and your constraints are not always satisfied, right? So an MLN is a set of first order formulas Fi, and with every formula Fi you have an associated weight Wi, right? And these formulas are defined over application specific predicates, and there are two types of predicates in MLNs. You have what are called query predicates and evidence predicates, right? And your formulas actually capture relationships between these two types of predicates. So for example here, query predicates specify in our example application, they extraction application, they specify the labels that you associate with web page nodes. Okay. So for example, here is a query predicate which says that node n is assigned the label name, and here node n is assigned the label address, right? And evidence predicates specify the content and structural features that you've actually seen in the data, right? So that's the evidence that your model has. So for example, has 10 digits n. This predicate will fire if your node n actually has 10 digits, or n1 n2 precedes n1 n2 is true if n1 precedes n2, right? So here are some examples of formulas in the MLN model. So in our application, this would say, well, if a node n has 10 digits, then it's very likely a phone number, right? And name values actually precede address values in a page. Okay, so now, so that was the basics for Markov Logic Networks. Now let's look at really how do you do inference in MLN models, right? So the probability in the MLN model, the probability of that a set of query predicates Q is true given some evidence X, right? These are your some evidence predicates that are true, is given by this expression here, right? Now here X is the your evidence predicates that are true. Gi are all the set of groundings for your formula Fi, and here this grounding here has a value of 1 if the grounding is true, and it has a value of 0 if the grounding is false, right? So this expression here is nothing but the weighted sum of all the ground formulas that are true if your query predicates Q and evidence predicates X are true, right? So this is the weighted sum of all the true ground formulas, right? Now inference in MLN models is as follows. You're given a set of pages here in our application, and these pages have a set of true predicates X What you're interested in is finding a set of query predicates Q star with the maximum probability, right? So basically you want finding this Q star is equivalent to finding a Q star that will maximize this expression, right? Which was the weighted sum of the true ground formulas, right? So it's easy to see that actually inference in MLNs is equivalent to weighted maxsat, right? And we know that weighted maxsat is NP hard. So MLNs do have a lot of expressive power in terms of providing you first order logic, but compared to your linear chain CRFs or hidden Markov models and so on. But you do have a problem with the computation side, right? Inference becomes NP hard. And the popular approaches are really to use satisfiability solvers out there. Max walk set is a very popular way of doing inference in MLNs. This is based on stochastic local search. Typically these satisfiability solvers work by randomly selecting some unsatisfied formula, and then they will probabilistically flip the truth value of either a random predicate in the formula or a predicate that would maximize the weight of all the satisfied formulas. Okay, so that's how the satisfiability solvers work. So they work at a very low level on all the ground formulas, and they're just randomly selecting unsatisfied formulas, trying to toggle the randomly toggling truth values of predicates and so on. Okay. Now training of MLNs involves learning these weights Wi for all the formulas Fi. So this is just like training in many of the other models, and what you are given is a small set of training data. These are basically human labeled pages, and what we use in our work is an online algorithm called margin infused relax algorithm out here, or MIRA, and it's an online algorithm, so it updates the weights every time it sees a new example. So every time you have a new example, the algorithm first infers what the label for that example is, and that's done using our own inference procedure and the current set of weights that we have. And if you find that the inferred label is different from the actual label for that example, then you update the weights, right? And you select new weights Wi prime, and you try to make sure that these weights are very close to the older weight, so you don't want the weights to change too much. And also with the new weights, you want the probability of the actual label to exceed the probability of the inferred label that was incorrect by a certain margin, right? So you just solve an equations, a system of equations here, and that gives you the new set of weights. Okay. So so what are the main contributions of our work, right? As I mentioned, Markov Logic Networks have been used before for information extraction, but they were applied to very specific domains like web forum for sites and so on, right? Our work, we use MLNs for really general purpose extraction from the web. So the schemes that I'm going to talk about can be used on arbitrary websites. They're not restricted to just web forum sites and so on. And one of the key key attributes of our work is that we're really using a very expressive models in terms of Markov Logic Networks for extraction, and this allows us to actually capture a lot of different kind of features, right? I mean, there's content features of nodes, there are structural features, and a lot of these structural features cannot really be captured by linear chain CRFs and so on. So as we'll see, some of the features are fairly powerful. They allow relationships and dependencies that are fairly long range between items that are spread apart in web pages. And by using Markov Logic Networks, we are able to capture both structural and content features in a single framework, right? In a lot of the previous work, what people would do is use content features to sort of do one pass and recognize some attributes in the page, and then try to do a post-processing phase where they try to somehow optimize the structural information also that we have, right? But clearly that's suboptimal, doing multiple passes in which you try to refine the labels. So being able to capture all the features in one framework, right, is really powerful, and that's very helpful. But clearly all the expressive power comes at a price, right? I mean, as we saw, your traditional satisfiability solvers that people use for MLN inference don't really scale to very large domain sizes and complex formulas, and I'll talk about that in our experiments. So clearly when you go to very expressive models, you have a problem with computation, right? So in this work, what we do is we really have a very fast graph-based algorithm for MLN inference, and this here in kinds of formulating this problem, we exploit semantics of the application and the structure of the application to make inference a lot faster. Okay. So let's look at what are the different kinds of formulas that we use in our work, right? So evidence predicates are of two types. There's content predicates and structural predicates. Now content predicates typically specify characteristics of attribute values in a node, right? So for example, has 10 digits, contains word road. These are all examples of content predicates. And content formulas connect content predicates and query predicates, right? So here, these were your query predicates, which are basically the labels that you're assigning to nodes. So for example, here you have, phone numbers have 10 digits, addresses contain the word road, and so on. So these are your sort of content formulas, right? And then we have structural formulas. So these are the ones that are more difficult actually to capture, because the previous content formulas are restricted to just one node. These capture long-range dependencies between attribute value occurrences within a page and also maybe across pages, as we'll see. There are three types of structural formulas that we use. Again, structural formulas will take your structural predicates and your query predicates and sort of link them together in a single formula, right? So precedence formulas essentially specify your ordering relationships between attribute values. So for example, this formula here states that name appears before address in your web pages, right? This predicate here is true if the position of n1 is either above or to the left of node n2, right? Now proximity formulas are again capture the fact that typically attribute values tend to occur close together within a page, right? When you look at web pages, you'll find that addresses and phone numbers, for example, appear close together. And alignment constraints are the final constraints that we have, the structural constraints, and these are between pages. So they capture the fact that attribute values occur at the same position across the pages of a template-based website, right? So that's where the template pages come in, because they all have the same structure, and so these attribute values occur at the same position across all those pages, right? So for example, if you look at this constraint, this formula here, it states that, well, if there are two nodes n1 n2 which have the same label, then they must be aligned. And aligned here means that they have the same DOM tree paths within the page, right? So this constraint here, alignment constraints, actually are between pages, and such constraints cannot really be captured by CRFs or many your linear chain CRFs and so on. So you need much more powerful and expressive models to capture constraints between pages and so on, right? Because these aren't adjacent anymore. And then we have hard constraints. These are formulas that are always true. So for example, simple things like a node can be assigned only one label, right? So if a node is a name, then it can be an address, or a node is an address, it can be a phone number, so on. And then we have contiguity constraints, and these are actually pretty tough constraints to handle. I mean, for most of the satisfiability solvers and so on. So many nodes within web pages, what we found is many attributes like address actually span multiple nodes, right? But in general, these nodes that have the same attribute label are contiguous, right? So that's an interesting property within websites, right? So for example here, what this formula states is that if there are two nodes n1 and n3 that have the same address label within a page, then every intermediate node between them also has the same address label, right? So that this formula is saying that nodes that have the same attribute label are contiguous in your web page, right? And this is a killer formula for MLNs, right? This is already cubic. If you have a page with 1,000 nodes, now you're taking all triples of nodes. So it's 1,000 to the power 3, which is already 1 billion groundings, right? So this formula here can generate 1 billion groundings in your Markov Logic network, right? And pretty much kill your satisfiability solvers unless you use some very clever tricks. Yeah.
So all these domains are bounded, right? So
right.
So when you say first order logic, it is actually propositional logic.
Yeah, it is propositional logic, except that you have to expand out what N1, N2, N3 are here, right?
So what exactly do you mean when you say more expressive?
Yeah, so it is propositional logic.
Right.
Yeah, so even propositional logic is very expressive, right? It won't capture.
What you're saying is that maybe perhaps the specifications are more compact or succinct.
Yeah. So you could specify it a lot more. So you don't have to. It's a very succinct way of specifying it. But it does expand into groundings, right? So in the end, what you have are groundings. The model allows groundings, right? And the fact is that there's no restriction on the kinds of formulas you can have. You can have any formula you want, right, that combines it. And in our application, we do have formulas of this kind, which are fairly, which can lead to lots of groundings, right?
But
Cubic number.
Integer constraints and things like that.
What's that?
Integer constraints, for example, because
integer constraints in what sense?
like x plus y is greater than equal to 3 or something.
Right. You could. This is anything with evidence predicates. Something's greater than something else. That's an evidence. That's a relationship, right? 5 is greater than 3. That could be an evidence predicate in your database, right? Yeah.
So I was just thinking the same thing that what you said about this being a killer predicate. Did you try writing out predicates for pages which are not template pages but like a list page where you have multiple records?
Yeah.
You have alignment and you want
Right.
one node and other smaller nodes sitting inside.
Yes. Yeah. You can extend this so that you'll have more formulas. It only makes the problem more complex, right?
Big formulas, right? So I was wondering if you tried.
Yeah, we haven't done it actually. That's part of future work. We didn't apply this to list pages, but you could develop. Right now, I'm just talking about single entity pages, but you could apply all this to list pages as well, right?
But the formulas will be very complex.
Yeah, so you'll have much more complex formulas and so on, right? So the trick here is again to the formulas are. It's all. This is all the formalism, but the question is when you do inference, nothing's stopping you from having very specialized procedures, right? The formulas may look very complex, but when you algorithmically want to explore the solution for inference, there may be a lot of domain knowledge that can be captured in your exploration, right? That's the trick here, right? So again, it'll become clear when I talk about how we do, how we enforce these contiguity constraints in our work, right? Because if you just gave it to a satisfiability solver, it was just going to croak, I think our stuff just ran out of memory and crashed. It just couldn't cope with pages with, with a billion groundings and so on. So some other software out there. Yeah, I think there are ways. I think Parag probably will talk about some of this in the next talk. There are lots of ways to make MLNs a lot faster by doing lazy evaluation and storing some things in more optimized way. I don't know if you're covering all that, but yeah, some of it. But this is orthogonal to that. This is really going into the logic of the application and really coming up with some very clever techniques that operate at a much higher level of abstraction, right? So again, that actually brings. Like I said, the satisfiability solvers like MaxWalkSat are really operating on ground formulas, and that makes it extremely inefficient because, like I said, ground formulas can be cubic in the number of nodes. So what we want to do here, really, one of the key observations that we make here are that our formulas have very specific structure, right? Our content formulas have only one node, and structural formulas are really defined over 2 nodes, right? So it's possible to capture all these formulas and constraints in a graph, in a very high level graph based framework, right? And what we show is we can reduce this inference problem to finding a maximum weight subgraph, right? And this stuff, I mean, there's lots of heuristics out there to find maximum weight subgraphs. Of course, it's an NP-hard problem also, but it can be done very efficiently. And specifically, every graph operation now actually maps to multiple query predicate truth value operations, right? So that makes it a lot more efficient, right? And so let's see how we construct the graph, right? So let's say you have your page nodes, there's a sequence of page nodes. What we do is we create a separate layer for every attribute AJ, right? So we sort of replicate this structure multiple times for every attribute, right? So now what you have is a separate vertex Vij, right, which corresponds to node Ni and and attribute AJ, right? And intuitively selecting this vertex Vij is equivalent to assigning a label of AJ to node Ni. Okay, so that's sort of the semantics of having a vertex Vij, right? And we associate weights with both vertices Vij and edges Vij, VKL. So here the vertex Vij has a weight which is equal to the sum of the weights of all the true ground formulas that contain node Ni, right? When Ni is labeled AJ, right? Because like I said, this intuitively selecting this node is equivalent to applying setting Ni, giving Ni a label of AJ, right? So we look at all the ground formulas that become true when Ni gets the label AJ. Similarly, for edges, you can again give weights to Vij, VKL, which is the sum of the weights of all the true ground formulas containing Ni and Nk when Ni is labeled AJ and Nk is labeled AL, right? And we can show that finding the optimal label assignment Q star with the maximum probability is now equivalent to finding the maximum weight subgraph in this graph that we have, okay? And it's fairly, there's some subtlety here which I've sort of hidden under the rug. It's there in the full version of the paper, but essentially the weights of all the true ground formulas containing a single node are captured in the vertex weights, and the weights of all the true ground formulas, the structural formulas, right, containing two node pairs are captured in the edge weight. So intuitively at a very high level, that's what's happening here. So between the node weights, vertex weights and the edge weights, we're pretty much capturing all the all the weights of true ground formulas, right? So if we find a maximum weight subgraph here, we are finding the sort of the label assignment, optimal label assignment Q star. Okay. So just a quick example to explain that. Let's say you have two nodes N1 and N2, right? And there are strings associated with these nodes. The first one is a 51 Laval Road, and here there's a sort of a phone number. We're looking at extracting two attributes, address and phone number, and you have, let's say we have two content formulas. The first one is that if address values contain the word road and phone numbers contain 10 digits and both have a weight of 1, structural formula here states that address values appear before phone number, and this also has a weight of 1. So in this example, your true evidence predicates are basically contains word road N1 because N1 there contains the word road, has 10 digits N2 because N2 is a phone number and precedes N1, N2. So that's your evidence predicates. Now clearly the constructed graph here, we have a pair of vertices corresponding to N1 and N2 and each attribute, right? And I put down the weights of these vertices and the weights of the edges here just to see how these weights are derived. Let's look at the ground formulas sort of involving N1. We have two ground formulas here. Now both these ground formulas are true if N1 is assigned the label address, right? And so this vertex here has a weight of 2. But if you assign N1 the label phone, right, then this first ground formula here becomes false because this is the left hand side is true because N1 contains the word road, but when you assign N1 the label phone, this one becomes false. So this vertex here has a weight of only 1. Now similarly you can derive weights for the edges as well. So again you have two ground formulas containing N1 and N2, and if you assign N1 the label address and N2 the label phone, then both these ground formulas are true, so this edge ends up getting a weight of 2. And if you go the other way around, you would assign N1 the label phone and N2 the label address, then this second ground formula becomes false because N1 actually precedes N2. So this edge actually ends up having a weight of 1. And we can also enforce these hard constraints. I have 5 minutes more? Okay. I'll just quickly go over some of the intuition here. Now, we had the single label constraint, right? So how do you capture the hard constraints in this graph-based framework, right? Well, the way to do the single label constraint is simply put an edge with the weight of -infinity between vertices that correspond to the same node, right? So now only one of these two vertices can be selected. So N1 can only get a label of either address or phone, right? So you can start capturing the hard constraints in the graph also. And the killer constraint, which was the contiguity constraints, right? So here we play some tricks. We consider all subsequences of vertices vertices in an attribute layer, and we coalesce them to get super vertices. Of course, this can give you n square sort of super vertices. So what we do is we actually prune out about 90% of those super vertices which have negative weights or which don't have very high weight, and we only keep 10%. So we keep a very small fraction of those super vertices, and these super vertices have a weight that's equal to sum of the weights of all the vertices contained in them. And by appropriately sort of adding -infinity edges here again with all other vertices in the same attribute layer, you can guarantee that only one of these super vertices is selected in every attribute layer. So you only have one sequence of nodes corresponding to a super vertex that's all assigned the same attribute label. So all this can be done at a very high level in the graph. You're no longer really trying to toggle predicate values and so on, which takes a long time, right? So this is semantics of the application that we have captured within the graph itself, right? Rather than letting a very low level SAT solver actually find the solution. So now here the maximum weight subgraph actually is this vertex and this vertex, V11 and V22, and the total weight is 6, right? So that's the maximum weight subgraph. That corresponds to assigning a label of address to N1 and a label of phone to N2. Again, we have a greedy heuristic. To compute this maximum weight subgraph, it just starts with an empty set, and then it keeps performing one of two actions to kind of increase the weight of the set S. So either you add a vertex to S so that this weight is the maximum, or you swap a vertex in S with another vertex to maximize the weight, right? So we have a bunch of experiments that we did. We have two data sets, books and restaurants, and books contains about 500 sort of randomly sampled pages from these sites here. The restaurant data set has about 100 randomly sampled pages from a bunch of other sites. Here are the attributes that we look at extracting for the book attributes. So it's name, price, date, number of pages, and for restaurant we look at the most restaurant attributes like name, address, phone, reviews, description, and so on. And interestingly, here are some of the content predicates that we actually use for extraction. So we look for large fonts for when we are extracting names, 4 digits for dates, maybe look for days in timing and so on. So these are the kinds of content predicates that are sort of used for identifying the various attributes. And of course, for reviews, we actually create a reviews dictionary that contains frequently occurring words in reviews text, and we have this predicate here which actually fires if the number of fraction of words in a node that overlap with the dictionary is larger than a certain threshold. So just looking at the sort of accuracy results, what we do here is, these are the F1 scores that we've plotted for the different attributes and the data sets. We first only consider content formulas, and then we consider, content formulas plus intra-page proximity and precedence structural formulas, and then the final column here is with content formulas and all sorts of structural formulas, including interpage structural formulas. So clearly, as you can see, for our MLN model, as you add more and more information about the structure as well, you start getting much better F1 performance, right? So you could just use content to try and label, attributes, and that's going to, not give you as good results as sort of taking into account even structural constraints, like name occurs before address, or name and address occur close together, and so on. So there's value in having the constraints, the structure constraints. Now the Max-Walk-Sat algorithm actually crashed when we ran it with contiguity constraints, just because of the large size of the groundings. And so what we did is, I think we used the implementation, the Beast implementation of Max-Walk-Sat. And so we ran it without contiguity constraints, and as you can see here, the accuracy numbers are pretty low, right? So basically it also tells you that hard constraints are important. I mean, things like contiguity constraints are very important to get accurate labeling of the data, right? And that's a place where your your satisfiability solvers can't handle those kinds of constraints. Yeah?
So the first column, did they have those constraints? The C one? No, right?
The first column, yeah, C didn't have that constraints. So this is only, okay, let me see. Actually, C had it. C probably also had it, right? It was only the structural, the hard constraints were there throughout. Yeah, so C, all these had the contiguity constraints. Okay, we could have done one without contiguity constraints also. Yeah, so this here we were looking at more how things change when we add structure, right? Get structural information. So I mean, basically the point is you do need models that can capture these, fairly, rich features, right? Same result for labeling accuracy on the restaurant data set. Again, adding structural formulas gave us better performance, and of course not having contiguity constraints does hurt the performance. Inference time, our graph-based algorithm is an order of magnitude faster than Max-Walk-Sat. So clearly there are advantages here. And we also compared with HCRFs, and here again is sort of the data point for where the HCRF performance on the test data set, on the test site is much lower than the F1 score performance that we had for our MLN model. Again, this point here is actually when we only took training data site examples in the test set, and as we keep adding more examples from the test site, the performance deteriorates. And we did this experiment because there was a paper on HCRFs from Microsoft Research Asia where they showed really good numbers, and we suspect that they use data from the training sites in the test sites to show their graphs. So it did fine, it did very well when you had your test data from your training data. But if you went to a new site, the performance is really pretty bad. So we suspected that, so that's why we did this experiment. Just summary, real quick. So clearly, I mean, hopefully you're convinced that building these knowledge bases can be useful for many web applications like search and so on. And clearly, extracting information, especially in an unsupervised manner from websites, is a huge challenge, and machine learning can provide solutions for doing this. Clearly, I mean, what I feel is an approach that uses very powerful and expressive machine learning models and machine learning frameworks like Markov Logic Networks clearly are useful to capture lots of different kinds of constraints and features that you encounter in practice in applications like this. So clearly what you need then is very fast inference algorithms, right? I mean, because the current inference algorithms just based on Max-Walk-Sat and things like that are just not going to cut it. I mean, they are not going to be able to scale just because of NP hardness and intractability and so on. So you do need to get into application semantics and structure for efficient inference. And clearly I think this is interesting research direction where you can try to say, well, if your formulas have a structure of this kind, then here are really some very fast algorithms for inference, right? I mean, so capturing that, so you could have now a general class of inference algorithms when your formulas have a certain structure, right? I mean, here our formulas had certain structure and we were able to come up with some very efficient algorithms. So yeah, I mean, there was a question on list pages, so that was sort of future work. We're looking at emails. We were doing all this at Yahoo. I'm not doing this anymore now. At Amazon, looking at other things. And then integrating records from different sites. I mean, data integration is also an important problem. So that's pretty much it. Any questions? I'd be happy. Yeah.
So basically, we were solving multi-level problems. I'm just wondering, can the mean cut based graph cut, mean graph cut algorithm be applied for this problem? Because in computer vision especially, we have mood mapping algorithms to solve multi-level problems. So I'm just wondering, can this mean cut problem instead of max cut be applied for this study?
Okay. Well, I don't know if I'm using max cut. I was using max weighted SAT, so okay. That was a different thing. But yeah, go ahead. Yeah, sure, go ahead.
So I guess if the edges are binary, there are no three-way constraints, then this problem exactly translates into two SAT problem, which is equal to mean cut. So you can directly solve it. It's no longer actually empty-high. So if edges are, if only your binary edges, because they have three-way constraints, so then it's not applicable. Then it's actually in P, because two SAT is in P. So then you can actually solve it. I think the issue is that, because mean cut has a polynomial transformation. Yes. That because you have three-way constraints, then
yeah.
So was the continuity constraint a problem because it was deterministic, or is it due to the fact that it had high support?
No, it was a problem because it involved three nodes, no triples, and when you start instantiating it, right, it just bloats up, right? I mean, if there and these web pages have about 1,000 nodes, you know, some web pages have more. So 1,000 to the power 3 is already 1 billion groundings, right? And many of the software packages store everything in memory, so you run out of memory, right? So that's the typical problem, is these things don't scale.